Hi, today we'll be talking about chapter 7 and 8. I put both of these chapters together because they really go together. They form the kind of theoretical underpinning for doing inferential statistics, which we'll be doing the rest of this semester. Um, so just to kind of explain a little bit in chapter 7. In chapter 7, they introduce the concept of sampling distributions. A sampling distribution is something that really doesn't exist in real life, but it's a theoretical construct that looks at what happens when you take a sample from a population. So a population is the entire group of objects about which you want information. And many times what you find in real research in businesses is that you can't really sample a whole population. For instance, if you are trying to determine the flame retardancy of children's sleepwear, what you do to do that is you actually hold it close to a flame and see how long it takes to ignite. Obviously, no one is going to buy children's pajamas with holes burned in the front of them to prove they're flame retardant. If you test tires, you're testing the life mileage of those. You can't test every tire. So we have to take samples. And it's very important that you can rely on the results of your samples. So a sample in inferential statistics, what we're doing is we are taking a sample from a population, and doing this, what we do is we compute a sample statistic from this sample. And this sample statistic or measure is used to make an inference back to the population. So if we conclude in our test of children's sleepwear that it takes 4 seconds in our sample for it to catch fire, then we would say that the whole population takes 4 seconds. And this allows us, again, to keep from sampling everything. So the sampling distribution of the mean, and I'm going to open up an Excel spreadsheet here that has some numbers on it just to kind of walk you through it. But page 217 in your book, he kind of explains this, and if mine doesn't make any sense, look at his. So what he gives you is an example, a very, very small population of 4. And he looks at the number of errors that each of these 4 people make. It turns out Carla makes 1, Bob makes 2, Ann makes 3 errors, and Dave makes 4 errors. So you can compute from your sample a mean and a measure. So when you take a sample, what he's saying is to construct the sampling distribution in theory, if you took all possible combinations, for instance, of a sample size of 2. So that's what I did. I sat down and I said, okay, if the first observation was 1 and the second observation was 1, I would have a 1 and a 1. And down, if I move down a little further here, easier to see, a 1 and a 1, the average is 1. So it corresponds with, the sheet in this other table I've created. If the first observation was 2 and the second observation was 1, that's 2 and a 1, that gives me a 1.5. So this creates all the possible averages, which is our sample statistic we're interested in. If I take the average of the averages, I did that somewhere, here it is, 2.5. And what I did is I put all these answers down here, the possibilities. I sorted them in order so I didn't have to do all that work. And I created this is nothing more than a frequency distribution here. So this is the number of observations I had of the, averages that equal 1, and the number of observations that equal 2, or 1.5, the number of observations that equal 2, and so forth. And if you create a histogram for that, this is not a really good histogram because I should have had the numbers closer together, I guess, but I guess since they're discrete numbers, it's okay. Anyway, you can see that this begins to look kind of like a normal distribution, this bell-shaped curve we've talked about back in chapter 3 and also in chapter 6. So this is kind of the theory, is that if you take a large enough sample, which they define using the empirical rule as being about 30, and if you don't know what the population looks like, and with the proportion, I'll explain that in a few minutes. But if you take a large enough sample, it's assumed that any sample you take out of that will look approximately normally distributed. Anyway, so that's kind of the theory. But again, read it over in the book and make sure it makes sense. The second part of this is what do we do with all these numbers that we just created? So he goes through several examples in the book. So the first here, in example 7.1, talks about what changes when you begin to look at inferential statistics. Since you're taking a sample, you remember our z-score formula said z equals x minus mu divided by sigma. All these are population numbers, population symbols. In our example, we substitute in the denominator for the standard deviation something called the standard error of the mean. So for this example, he says, suppose we have a sample size of 25 and a standard deviation of 15. This formula for the standard error of mean says take the standard deviation and divide it by the square root of the sample size. So the size of the sample impacts the size of the standard error of the mean, which impacts your z-score formula, which changes the area. So in our case, we've got 15 divided by 5, which is the square root of 25, which gives me 3. If I had had a sample size of 100, I would have had 15 divided by 10, which would have been 1.5. So you can see the sample size impacts the size of this. So you just have to remember from here on out this semester, if you're using the z-score formula and you're finding an area, which you will do frequently, you should always use the standard error of the mean in the denominator of your z-score formula. The other thing that I want to talk to you about is computing areas using the standard error of the mean. So you can use PHStat for this, or you can do it by hand using your tables, either one. But the computation, this again, example 7.3 in your book, he changes the sample size to 100. He has the same 15 for the standard deviation, and the mean, what they think is in the population is 368, it's grams or something like that. So they ask you to find the probability that the sample mean is below 365. So here's your z-score formula with the adjustment here in the denominator. So we've got 365, which is our x bar, what we're looking for, minus what we think is the mean in the population, divided by the standard error of the mean, which is 1.5. So minus 3 divided by 1.5 gives us a negative 2.00. And you would go to the normal distribution tables and you would look that up. You can also use PHStat. I've got PHStat open here, so let me just go to PHStat and probability distributions. And remember, you did normal for your homework. Our mean in this problem is assumed to be 368. Our standard deviation is, we are going to use the 1.5. So use the standard error of the mean. And what we want is actually what comes checked here. We want to know the probability that's less than 365. And I just say, okay, and it creates a whole new page. And there it is. So the probability of that occurring is about 2.28% chance. So there's your answer. Or again, you could look it up, you know, with the negative 2.0. Anyways, that's how you do that. Anyway, and then let's see. And then he has one more, I think. Excuse me, I made it a little bigger than I intended to. So, you know, another thing, again, you did this again back in chapter 6, you computed an interval for a mean. In other words, 95% of the observations, or around what values, you know, comprise 95%. So here's another example he does in 7.4. N equals 25 here. Standard deviation of 15. We're back to the first example, and the 368. I don't know why he keeps changing it in the book, but he does. So the interval that includes 95% of the observations, we're going to assume that we use a normal distribution here, because that's all he does in this chapter. So you would need to find the z-score for 1/2 of the 95%. So a z-score for the area 0.0250 will give you a z-score. And if you look that up in the book, you'll find that it's a negative 1.96, And because this is a symmetrical distribution, on the upper side, here's the upper, here's the lower, so it's just a plus here, and you've got a negative z-score and a positive z-score. So a 1.96 on the upper side. And you come up with these numbers. You also can do this using pH stat. Again, go back to probability and probability distributions, and here's your normal again. Again, my mean is 368. My standard deviation is the standard deviation of the standard error of the mean, which is 15 divided by 5. Right, 15 divided by 5, which is 3. And we want to know values for a percentage. I'm going to uncheck that one box, and we want to know 95%. And it should figure that for us. And you'll see that we come up with the area from 362.12 up to 373.88. And again, this is exactly what I figured out using my calculator and looking at the book and looking up the z-score and then looking up that area for that z-score in the normal distribution. So anyway, that's how you deal with a mean. You also, and they talk about doing proportions. Proportions are kind of different. When you dealt with proportions back in chapter 5, we used a discrete distribution, which was a binomial distribution. And you can, under certain circumstances, if your sample size is large enough, assume that the empirical rule applies, and you can use a normal distribution to look up areas. So the rule is you can use a normal distribution as long as your sample size times your proportion is greater than or equal to 5, and in time, sample size times 1 minus your proportion is also greater than or equal to 5. So for instance, in this example that they've got down here, they have a sample size of 200 and a proportion of 0.73. So 73% of 200 is what, 144 or something like that. And then 1 minus 73 is about 20%, a little more, you can figure that out. And 20% of 200 is definitely greater than or equal to 5. So you got to check it and make sure you're okay. Once you do that, you have to compute the standard error of the proportion, which looks a little different. So the standard error of the proportion says take the proportion, down here it is, multiply it times 1 minus the proportion divided by the sample size, take the square root of the whole thing. So in this particular problem, the standard error of the proportion is 0.0314. So if you want to find the probability of more than 80%, again, you can do it using your tables. Just substitute in the standard error of your proportion, the 0.0314 in the denominator for the z-score formula, and use proportions. So you've got 80% minus 73% divided by 3.14%, and you get a z-score of 2.23. You can do this in pH stat also. Just use normal distributions and plug in your proportion. So your average is 0.73. You put the proportions right in. Standard deviation, you put in your 0.0314. And I want to find more than 80. So I'm going to check this box, uncheck that one. And more than 0.8. And that's all I've got to put in. And I say okay, and I should see the same proportion I would have gotten had I done it, by hand. So you can look it up in the tables and find that 41.118% or not. Anyway, that should kind of get you, through the actual computations in chapter 7, but read it over carefully. Take care. Bye.